with that, I think let's move on to this to the technical talk, which is uh, on basically radiation and nuclear materials research. And the basis of this, like I said, started when I was a student in as a PhD student in BRC. And so in BRC, I after Dr. Godwal retired, uh, Dr. Kailash basically became my supervisor, because he was also the head of the accelerators in BRC, and hence he provided a lot of support in accessing a lot of these facilities, in providing guidance in writing thesis, in discussing things. And so it's a very interesting that you end up doing something that you never thought that you would start with. Okay, so so the basis of this is we know that energy is one of the most critical sort of important grand challenges in most of the countries around the world. And here is a map of the world where you're seeing the amount of sort of energy that is required, will be required over from 2016 to 2040 in million tons of oil equivalent, and 1 million ton of oil equivalent roughly is about 11 megawatt hours, or something like that. So, and you can see some of these countries like India and China will see a major growth, and hence a major demand in the primary energy. And this is because of the economic growth that is expected in India and China and other Southeast Asian countries as well. So, and I think in around the current population is about 7.4 billion, but it's expected to go to 9 in by 2040. And with the population growth, and there has to be economic growth. But when you have economic growth, you also have a huge demand on the electricity, on the electric supply, right? And so this is in terawatt hours how much India and China and other developing countries will need going forward to see this much growth rate. And so obviously, but in the other scenario that we live in is climate change, right? And in climate change, what you have is if we have lots of greenhouse emissions. So currently, without any, so we are here, for example, in 2017. So let's call this as 2020. We aren't too far. If we need to, on this scale, you have the GDP, and on this scale, we have the carbon emissions in gigatons. And if we with the current policies, we can still achieve this growth over here, but it would increase our carbon footprint also. With the new policies like Paris Agreement and other things, we will probably reduce our carbon footprint to what is expected. However, the best way to go would be towards a sustainable development, where you do see economic growth, but at the same time see that our carbon footprint is reduced. And that's what we mean by sustainable development. Otherwise, we cannot keep a sustainable growth. And this leads to what we call in the energy field as the trilemma. And so the energy trilemma is that of sustainability, cost, and reliability, right? So you need you need a mix of energy sources that are cost effective, that we have enough of those, so we can sustain it for quite a long time, and that are reliable, that do not shut off and on, that have a very high capacity factor. And this has been always a major issue, because, for example, let's talk about solar, right? So if you have a solar wind turbine, you can imagine, a solar farm. We know that sun is going to be there forever, right? And so that is a sustainable source of energy. But sun doesn't shine always in the UK, so it's not a really reliable source of energy. And likewise, you can take examples of wind, nuclear, and other sources, and we will get to that in a second. But for a take-home message over here is if you are working in the field of energy, anywhere in the field of energy, you will be you want to have technologies and a mix of technologies where you can show sustainability, reliability, and cost effectiveness of your energy mix. The UN also states similar goals, and one of them, the UN has different lots of these 17 sustainable development goals, and one of them is affordable and clean energy, which is basically to ensure that everybody has universal access to affordable, reliable energy. And hence we can do that by increasing the renewable share in the energy mix, and so on and so forth. So these are different sort of UN goals towards how we can get a sustainable growth. So the different energy technologies that are of interest to me are, here is a picture on the top left of Crosby Beach, and it's not a naked man, it's just a statue. These are all iron statues on a Crosby Beach, which is, I think, about a mile or two away from where I am right now in Liverpool. And there we have huge wind farms, because Liverpool and other coastal areas have a very well established infrastructure for wind, for energy from wind, basically. So you'll see a lot of wind turbines everywhere around UK. And then you have a big solar farm at the bottom left, and then on the middle right you have a nuclear power station. So let's compare them. And this, I think, the idea for this slide came from one of Dr. Banerjee's talks in TED. So if you want 10 gigawatts of energy, then it would take about 500 square kilometers of wind farm, about 400 square kilometers of a solar farm, and just about 2 square kilometers of a footprint for a nuclear reactor. But that's not that striking, considering India is a big country, US is a big country. It's very important when you have countries like UK that have a very small land area. However, the capacity factor, which is how much energy you can extract versus how much the technology is capable of, in simple terms. So wind farms, for example, will have a capacity factor of 25%. What that means is that if wind blew with the same rate, with the same speed all year round, and all the wind turbines kept turning, then you will generate 100% of the capacity for which all the turbines were made for. However, wind does not blow all year round, and hence the capacity factor is not 100%. Likewise, sun does not shine all day. That's a natural phenomena, we know. And also sun shines less in some of the European countries, more so than some of the Asian countries, right? So, or in the equatorial belt. And so hence, again, the capacity factor for solar is quite low. However, if you take nuclear, from 1 gram of uranium-235, if you burn that much per day, you'll get about 1 megawatt of electric power per day of energy. And that's about burning equivalent of 27 million kilograms of coal. And so the capacity factor, and once you start a reactor, the power is steady. If you download this data from any of the databases on different energy as a function of time along the year, you'll see that there are dips where in solar and in wind, but there are no dips in a nuclear power on the grid, because once the reactor starts, it almost gives you a steady state power on the grid, and hence your capacity factor is close to 90% in nuclear. That doesn't mean, and we all know that doesn't mean that nuclear is the best technology, but it is still one of the highest efficiency energy technologies that we have. The problem we all know, and is is that of the safe operation, and we'll get to that. So here is again a list of different capacity factors. This is a plot of how many new operable nuclear reactors are there in India versus what were, I think, in the early years, and obviously we are increasing. These were the currently operated different sites where different civilian nuclear reactors are currently operating in India. And then these are the new ones that are being planned, and some of them are under construction. So there's a huge effort in India and China and other developing countries in the Asian continent to increase the mix of nuclear to its energy mix. And this is a nuclear fuel cycle for students, just to give you a small brief where my research would fall in a nuclear fuel cycle. If it's open-ended or if it's close-ended, it starts with mining of uranium and making it enriched, because natural uranium has about 0.7% of 235 versus 99.3% of your 238, which is non-fissile, and we need to increase the fissile component. But in India and other in Canada, we operate reactors that can take low enriched uranium, and those then go into the reactor as a fuel. The reactor operates, you get energy. Once you have extracted enough energy, and that's again just a quote unquote statement. We'll see why in a second. Then you remove the fuel, which becomes spent fuel, and it's stored in casks or in pools to cool down for a significant amount of time, and we'll see why in a few. And then you reprocess it, or you deem it as nuclear waste if it's an open-ended cycle. If it's a closed-ended cycle, fuel cycle like in India, then we reprocess it and make new fuel out of it and put it back in the reactor. And then the rest of the unwanted sort of spent fuel, it goes towards disposal. And so we can clearly see from here that why nuclear is an expensive affair. In fact, the actual cost of a reactor in today's day, at least in the UK, is close to 5 billion pounds. But it amounts to close to 20 or 25 billion simply because of the safeguarding of the nuclear material and mining and other aspects of it. And there are other experts in this group, like Dr. Mukherjee and Dr. Kailash, who know more about these than I do. I'm just talking from a material science perspective. So a simple reactor for the students, just to give you a quick intro, is basically, it's like a kettle. You produce heat in the center, the water boils, steam goes and turns the turbine. The cooled water comes back, and then again you generate steam, and that's how you generate electricity. In a pressurized water reactor, or in what you have is you have a pressure vessel, you have the control rods which control the reactivity of the reactor, and then you have these tubes which are called fuel elements, and we'll see the actual pictures of these as we go ahead. These fuel elements comprise of a cladding, which encapsulates the actual nuclear fuel. Okay, and then basically fission happens in these rods that generates energy, and you get steam, you turn turbines, and you generate electricity. This is a very simple schematic. And so where my research falls is trying to understand how we can operate reactors more safely, because it has a unique environment, unlike other technologies, let's say aerospace or any other technologies like mining. We go to extreme conditions, but nuclear is a totally different environment. And that's why we need to understand materials in these conditions and what these are. That's the next part of the talk. I just wanted to ask all the students if they are still with me on the talk, or if they had any questions, or if they prefer to ask it at the end, I'm fine. But if you want to ask now, then it's fine too. So please interrupt or write in the chat so that Nainesh or others can tell me if I have to stop and answer a couple of questions before I move ahead. Okay, so hence nuclear material science, because so what I primarily work with is these type of these components, not the whole reactor physics, but I try to look at what happens to these different fuel elements and different parts of the reactor and in the nuclear fuel cycle as we go. So fuel element comprises of these long 4-meter long cladding rods. These rods are made up of a zirconium alloy, okay? And these are 4-meter long, about 10 millimeters in diameter. And these rods encapsulate the fuel, okay? And we'll come to that in a second. And over time, this is a photograph looking down in the reactor vessel, where you had straight rods becoming slightly buckling. And that happens because of a reason of a physical phenomena that is happening. And we'll see in a second. This is a question to the students on the talk. Any idea how many of these 4-meter long rods would there be in a 1,000 megawatt reactor? Any guess? You can unmute and just shout out, I guess. That's what I'm asking. Any guess? 10, 15, 20, 30, 1,000? So there are approximately 50,000 of these in a 1,000 megawatt electric power reactor, roughly. And that has that puts an extreme pressure on manufacturing, in safeguarding and in operation of these reactors. And we'll see why. So that's the cladding. Okay, the fuel that goes in the cladding comes from obviously from mining a mineral, and then converting that into a fuel pellet, which is uranium dioxide. And this is a small crystal structure of uranium dioxide. I remember Professor Bhattacharya used to teach us crystal structures from Kittel, and I almost hated it, basically, not because she taught, but because I just didn't like crystallography. I just didn't like crystal structures. It was too confusing for my little brain. So what I ended up, but my fate didn't pulled me back, and I did start studying crystal structures for a living. So don't ask me how it happened. It just happened. So the fuel is made up of uranium dioxide, okay, where uranium is uranium-235, one of the fissile isotopes, is where that undergoes fission. Okay, and there are about.
I think there is a question. I think there is a question. Yeah, somebody has raised hand.
Okay.
So you can unmute yourself and ask, please. No? Okay, carry on.
Okay, no worries. Because I cannot see them, so please prompt me if somebody wants to ask a question. I can pause for a second. Yeah. It's a good break for everybody to absorb the material that we're talking about. So there are about 18 million pellets in a 1,000 megawatt power electric power reactor. Just so you know. So this is the scale at which we are looking at. When we talk about a typical power reactor. But the problem with the fuel is this: you want a fuel to kind of the best property you want in a nuclear fuel is obviously it should fission, but in addition to that, since it's generating heat, it should be able to lose heat, right, quite quickly. It means thermal conductivity should be extremely nice, and I don't know why, but we are stuck with uranium dioxide, which has one of the worst thermal conductivities of any material to be used in a nuclear reactor. Okay, there are historical reasons why, but we won't go into that. But just so you know, uranium dioxide has the worst property at which it is expected to be best. Okay, so this shows that so the pellet is about 1 centimeter in diameter, and in just that, half a centimeter in radius, there is a temperature gradient where at the center of the fuel pellet, it's about maybe 1,000, 2,000 degrees and above, and just half a centimeter outside, it's close to 300 degrees Celsius. Okay, and so that's huge gradient in the thermal, sort of profile. That leads to migration of pores, and this is a cross section of a fuel rod, where you see the outer periphery is the fuel cladding, and then the inner one is a fuel pellet. This central void is because I think this is a Magnox fuel. It has fuel which has a hole in the center. It looks like a donut. And then because of the thermal gradient, it develops these enormous microstructure changes, which then obviously changes the thermal conductivity. Thermal conductivity changes, your fuel performance changes, your reactor operation takes a hit in direct sense. And so then after when it goes in, it's nice and shiny like this. When it undergoes fission, you develop lots of bubbles, gas bubbles that make the fuel porous. You also develop these metal precipitates, which are fission products in some way. And then that leads to an interesting chemistry, right? So you start with UO2 somewhere over here. This is a plot of pure metal. And if you oxidize the pure metal, you go to MO4. I hear some, yeah. So if you have a pure metal and if you oxidize it completely, it becomes a metal tetraoxide, basically. And in the middle, when you change the oxygen stoichiometry, it goes from anywhere from M2O3 to MO3, and that's what happens to the fuel. It actually becomes hyper stoichiometric, and when your fuel becomes hyper stoichiometric, it changes its thermal properties. And so understanding these non-stoichiometric oxides is one part of my research that I do. Now that was the fuel. Fuel after operation becomes spent nuclear fuel. And in a spent nuclear fuel, you have lots of fission products, because UO2, uranium-235, gives probably on the periodic table, it can give you anywhere from gallium to gadolinium as fission products. And there's a peak in those two fission products. Somewhere around xenon, iodine, cesium, and strontium is where you have the peak, meaning the yield of these fission products is more than the others. Okay. The spent nuclear fuel is either stored in a cooling pond or in dry casks, because you have species like cesium and strontium, which have half-lives of about 30 years or so, and that we'll see what happens because of those. So, and then the fission products obviously can also form new compounds in the fuel, and so your fuel properties are changing as a function of time. Now, what you're left with is lots of waste. Well, it's deemed as waste in lots of countries, and if you reprocess it, your level of waste goes down. But you have different types of waste. One is called as high-level waste, where the activity is very high, to low-level waste, where the activity is significantly low. And it goes as a function of time, which is better shown in the next few slides. And this is the typical waste inventory in the UK. I'm sure there's a similar plot for in the Indian context as well. And so here is your spent nuclear fuel, coming from spent nuclear fuel, the waste portion, which is about 70%. I'll move on quickly to give you why nuclear waste is so significantly difficult to tackle, because If you look on this plot, this is quite a complicated plot, but I'll try to explain it to the best of my ability. Here you have activity, which is radioactivity, and time, which is in half-lives roughly, okay, for different isotopes. What I want you to draw your attention to was these alpha decaying. So these ones, cesium, strontium, they decay by pure beta, which is high energy electrons, and they decay in let's say 100 to 150 years, okay, and they become stable roughly. But the alpha emitting nuclei, their activity goes on for more than 1 million years. Now, I think the rough age of the Earth is about 4-point-something billion years, and so some of these isotopes, like I think thorium, the ones in the thorium series, thorium-232, has a half-life of 10 to the power 10 years or something. And so some of these other nuclides, which are actually man-made, so uranium, plutonium-239, technetium-99, neptunium, these are all man-made isotopes that are created after fission, and they are there forever, basically. And so what all of these things are releasing is a common thing, which is radiation. Okay, when the nuclear waste comes out, you mix it with glass or a ceramic, you put it in these casks, and they stay in dry storage until the plan to geologically dispose them, maybe 1,000 meters down the ground. And so with that, I think I've sort of given you an overview of the different stages in the nuclear fuel cycle. But one of the most common things in all of these different stages is radiation, and radiation leads to destruction of materials starting on an atomic scale, and that goes up right away to macroscopic scale. Okay. So this is a blank slide, so we can pause and sort of summarize what we've so far discussed. And if the students have any questions, I'm happy to kind of have a small discussion at this point and then move on to the last part.
Hello.
Yeah.
I have a question. Hello.
Yeah, I can hear you.
Yeah, good. So longer the half-life,
yeah,
slower rate of radiation is much less. Whatever the quantity Q is there, it is distributed for millions and millions of years.
Yes.
So hence it is safer to handle it, maybe for longer time, but the quantity per unit time is much less because of dispersal in time. Am I correct, sir?
Yes, the dispersal in time is the quantity is less, but still the type of radiation it releases, which is alpha, and the recoil particles of alpha, which we will see in the next part, that causes a huge amount of lattice destruction that then leads to changes in the property, at least in the nuclear immobilization, from the nuclear immobilization point of view.
I agree, but the number density per unit time is much less. So yes, it may depend on the situation. It could be self-repairing, or we may be able to tolerate it, perhaps.
You're right. You're right. Yes. And you're absolutely right. We are seeing some of the glasses that it will self-repair itself over time, or may not. And that's absolutely right.
Thank you.
No worries. Any other questions?
I have a question.
Yes, please.
Could you elaborate a bit more about the geological disposal of the waste, nuclear waste that you talked about?
Yeah. So again, this is a little bit out of my technical area, but so geological disposal is supposed to. So the first part is you immobilize the waste in a certain matrix, which is more stable, let's say glass or even better ceramics, and then we basically are finding a proper site where you dig deep trenches, I guess, and you put them in the casks, and then they will be left over there forever. At least that's a broad, rough plan, and probably Dr. Kailash or Dr. Mukherjee can kind of add on that. Currently, I think only Finland has this sort of a blueprint for a geological disposal site. We don't have it yet, but that's just my knowledge from last 10 years ago. Because you need a site which has a certain mineralogy, a certain geochemistry, and certain stability to sort of keep this waste intact without having the radionuclides migrating or leaching out in with water. And actually, studies have shown that some of the microbes actually can take on these nuclides, bacteria and microbes that can actually then transport it all over. But that's just the latest one. So that's my rough or a brief account of the geological disposal sort of side of things.
Mm-hmm. Thank you.
Yep. All right. So if there are no more questions, then we can sort of move on to the next part, which then naturally need. So my main interest in the nuclear material science side of things.
I have one more question.
Yes, sir.
The last question. I am researching. My name is Professor Karkera. I am researching on taking energy from gravity power. I call gravity acceleration, gravity force, gravity power. So I'm researching on that. Hopefully, within a year's time, I must be able to make, hopefully I can make one prototype. So we can take energy from the gravity force. Very interesting concept. So there is, without any fuel, we can get electricity virtually. Of course, there are number of issues which is nearly sorted out. So I name it as gravity power. All force fields can create power, and gravity is one of them. It also leads to the final theory. The universe has come from nothingness by self-creation. So that is ultimate anyway. I'm not worried about that. Immediately, it is a clean energy. Thank you, sir.
Yeah. No, thanks for sharing that. So, so what type of radiation are we talking about, right? The very first examples where Henry Becquerel basically saw an impression on on a fluorescent photographic paper with which had uranium-bearing salt. That was our first impressions, and then I think somewhere around 1920s or 1940s, Wigner pointed out that we are running these reactors that have energetic particles. These energetic particles can obviously interact with the materials in a way that the interaction is on an atomic scale. And when we know from 101 material science that structure has a direct bearing on the properties of materials. So if you damage the structure in some way, then your properties will change. We know this from even band theory of solids, which basically we've learned during our master's years. If you dislodge an atom from its own position, you change the band structure of these materials. And Wigner pointed out this in 1946, and very much so. The very first sort of one of the nuclear accidents that was supposed to be was going to be a big one was if you know was a wind scale accident, and that was because UK still operates reactors where the moderator is graphite, and when you cause radiation damage in graphite, it actually is stored as energy in graphite, and after some time it can be released as heat, and that has really huge consequences. Just to put in context, this amount of stored energy over here that is shown is equivalent to a few lithium-ion, more than a few lithium-ion batteries, just so you know. Haven't calculated, but I think there is a number on it. So it's pretty huge. And this is just from radiation-induced displaced carbon atoms in a graphite lattice. And obviously we know all these ones, which we grew up with in some ways, but that's not what we are going to talk about today. So the first radiation we are interested in is neutron. A neutron comes in, it imparts its energy. A neutron can be anywhere in this energy range. So this is a question to the students. What is the thermal energy of neutrons? What is the room temperature energy in electron volts? So we call all the power reactors as thermal reactors for a reason, because they have thermal energy. The neutrons that actually participate in fission actually thermal neutrons, meaning the energy is about 25 milli electron volts, somewhere over here. And these have a large displacement cross section. Okay, meaning they can cause lots of displacements. Okay, and then as you go higher in energy, you enter the fast neutron regime, and there again the damage cross section is higher, meaning the displacement cross section, meaning the possibility that the neutron will impart its energy to a target atom and make it move. Okay, and so if you imagine a perfect lattice, which is all these circles are each of full of atoms. Okay. The most simplest defect, or the primary defect that you can cause in a material, is an interstitial. So you remove an atom from its own site, you put it somewhere far in an interstitial site, and it becomes an interstitial atom. And and when you have more of neutrons coming in, they will cause more of these primary knock-on atoms, which then move slowly again. So the neutron imparts its energy to one of these atoms in the target. The target atom moves, which is a recoil, and then they will further cause more displacements. And hence you create more and more and more interstitials as radiation comes in and hits the materials, so to speak. And then if you heat the material, which is the conditions right conditions available in a nuclear reactor, right? So you add heat to it, all these interstitials can move. They move around, and interstitial mobility is pretty fast, faster than the other component of that defect, which is a vacancy. Sorry. And when they move and they agglomerate, they form something called as an extended defect, which is a dislocation loop. And you're left with a vacancy. Again, over time, these vacancies move, and you are left with an empty space in the lattice, which is called as void. And if you make a good TEM micrographs, and you take an electron microscope and you observe it, you can actually observe these white spots that look like bubbles are actually vacancy loops in sapphire, in alumina. And then these are your dislocation loops in iron, which is steel, essentially steel. And these lead to actually growth, macroscopic growth of materials. So here you have on the left-hand side a rod of a certain length before it was used in a reactor, and after it was irradiated with neutrons in a reactor for a certain amount of time. You can see that there is a macroscopic growth in length, and this has almost nothing to do with the fact that it's heated, but it's everything to do with the radiation-induced void swelling that you can get. Now imagine that the swelling is on an atomic scale, but imagine that happening all along the 4-meter long rod, right? And there are 50,000 of these rods that undergo this swelling. And from a simple reactor physics perspective, the flux of neutrons is very well, sort of controlled. They want the flux of neutrons to be uniform along a certain length of these rods. And when you change the length of these rods, the neutron flux profile fluctuates in the reactor. What that means is that your reactivity of the reactor fluctuates, which means then your operation is no longer going to be as stable as it was. Okay, and here is another photograph on the right-hand side where you have all these a whole fuel bundle with different fuel rods which undergo radiation, and some of them you can see have popped out because they've changed lengths due to radiation-induced swelling. So I hope this demonstrates that at an atomic scale phenomena can lead to a macroscopic disaster or macroscopic scale observations, real change. And hence that could lead, because the rods are constricted on two sides, it could lead to buckling of these rods. And obviously then you change your flux profiles. So now the neutron came in, it'll be absorbed, it'll cause fission. So uranium-235 splits into two fragments. Typically, the energy of these two fragments is between 70 to 120 million electron volts, and the masses of these would be anywhere from gallium to or well, these are very fast-moving particles, right? And so when they pass through solid, they quickly ionize. And I think some of these senior professors might have worked with something called as a cloud chamber, where you had an alpha source, the alpha particles are being shot, and you have nice, beautiful tracks that you can see in the gas. And likewise, these fission fragments pass through a material, and what they do is they create ionization, but this ionization is in a very, very tiny track. It's a very tiny zone. It's about 3 to 4 nanometers in radius. And that leads to an enormous change in the temperature, about 4,000 to 5,000 degree Kelvin, but in a few femtoseconds, not for a few seconds. Okay, so hence we call it the thermal spike. We get local melting sometimes, and then your structure changes. You can see in micrographs as these tracks, and if you do an atomic scale sort of transmission electron microscopy, you can get an atomic resolution image of these tracks over here. And I'm trying to point out on the bottom left micrograph. This is taken from an oxide, which is called lithium niobate. And these ion tracks are from single fission ions going through these materials. What that does to macroscopic properties is that you have a huge volume swelling that over here that leads to residual stresses in materials. And when you have residual stresses, it's not good for operation. Some of the natural fission tracks are also seen, because you have spontaneous fission going on in minerals, and that leads to these ion tracks as well, which is basically the reason the simple reason you see contrast is you take a glass and if you basically pulverize it, right, make it powder, it's no longer opaque, it's no longer transparent, it becomes opaque because you have created defects. And for the simple reason, you see these contrasting color contrasts in optical micrographs, in electron micrographs, because light cannot pass through, because the atoms in those places are basically displaced or change in refractive index. Okay. Coming to spent nuclear fuel. In spent nuclear fuel, you have some fission products like strontium and cesium, which decay by beta in the first 30 years. And when electrons pass through materials, they cause lots of ionization. And in these barium borosilicate glasses, which are used as nuclear waste immobilization in India, they cause these different defects that lead to changes in their stability. What I mean stability, you want a nuclear waste encapsulating material which is absolutely leach resistant, meaning if you put it in water, in high acidic water environment, it should not degrade, it should not leach out. Okay, it should not corrode. And these defects either enhance or degrade the leach resistance, which is the durability of these glasses. This waste is going to be there for forever. And so the number of displacements per atom that it does, let's say in this case, it's a MOX fuel, it's enormous. And when I say 1 dPa is that if you have a material that is irradiated, all the atoms in that one, let's say a square cube of material are displaced at least once. So that's 1 dPa, meaning all the atoms in that volume are displaced at least once. Now, if you go to high alpha activity over maybe 10,000 years, you have at least 100 dPas, which means that each atom has been displaced 100 times. And you can imagine what that would do to the properties of the waste matrices. The last one is alpha decay. Some of these plutonium like waste particles or waste nuclides, they will emit an alpha particle, which is about 4 to 5 MeV. And obviously in the process, it will convert itself into a daughter nuclei, which has a recoil energy. It's something like a gun effect. So when you shoot the bullet, imagine that the bullet is alpha particle, but then you have a recoil of the gun. That is the effect that the uranium-235 has. You can see that the energy of uranium-235 is very slow. The alpha particle is very fast. So the damage cross-section for the slower moving particle is higher because it's very heavy, it's large, and it's entering a room and it's moving slowly, so it can interact with everybody around it, right? Whereas if you're moving, if you are of low mass, you can move very fast to the room and you won't be having time to interact head on with people, right? So hence the uranium-235 basically causes lots of displacements, okay? And over time, you can actually see something like this. So this is a mineral called monazite, which was doped with plutonium-239, which releases alpha particles and recoil nucleus. And over time, you can see such particles shattering off of these single crystals that have been there for quite some time. And this is just a radiation-induced, degradation of materials, so to speak. And over time, obviously, you have accumulation of helium, and this helium will be accumulated in crystalline matrices. So that will lead to volume swelling over many years. But all of these, most of these phenomena, at least on the nuclear waste side of things, will happen in thousands of years, or in hundreds of years, or even in the whole lifetime of a reactor, right? Which is not a single, which is more than about 30 to 40 years of lifetime. But if you want to study these radiation effects in the lab to qualify and to discover new materials, you need to accelerate this damage phenomena or this damaging events, right? And that's what I use. I use accelerators like this one and the one in the next slide, which I've used for my PhD purposes. So and then you have a similar accelerator in TIFR, which I had almost started using. And then there's one more in BRC, which is a 6 million volt tandem, which I never got to the point to use. But what we use is energetic ion beams to sort of simulate these radiations that you have either in a nuclear reactor, in a nuclear fuel, or in a spent nuclear fuel, or in a nuclear waste scenarios. So I hope I have tried to make a point that you have lots of different types of radiation in which these materials are under operation, and these radiations cause atomic displacements. These atomic displacements lead to changes in mechanical and chemical and physical properties. And most of the time it's degradation of these properties. Hence, you can't use these materials in service for a longer time, which you want them to. But again, you have a mix of all these radiations. So when you're doing a science, when you're doing science, you almost want to take a reductionist approach, unlike engineers. And so you want to reduce your problems and pick pick your poison, so to speak, right? So with ion beams, I can say, okay, I'll go to IUSC Delhi or in TIFR and choose a 70 MeV iodine ion and shoot it on my materials, and then see and study how fission fragments would cause damage. I can go to IUSC Delhi and use a low energy ion accelerator and say I'll use 100 keV of a certain atom or an ion, and then you can shoot that on your materials and then see what damage it does to your materials, right? So you can then say this is damage that is reminiscent of or similar to of an alpha recoil or a neutron primary knock-on atom. Okay, so we choose different radiations, and now we have, over the last 50 years or so, people have now joined beam lines. So then you can bring 1, 2, 3, 4 beam lines together and have all different types of radiation coming synergistically together. And you can then say, what happens if alpha plus gamma plus beta, all of them are happening at the same time? And these are different accelerators I've used over the years. We won't go into accelerator operation as of now, because there are probably better alumni who can explain the accelerator operation than I am. And then you can actually heat your sample. Like in this case, you can heat your sample at a certain temperature and then study how defects would evolve. So that's one extreme environment, and I can pause for 2 minutes to take any questions if you have on that end. Nainesh, how much time do I have? Can I?
Yeah, I think so. You can finish it in 5 minutes because it's
okay.
16.
Yeah, that's fine. Yeah, so last few slides and then I'm done. So so then I'll move on to the last one, which is corrosion, which I didn't want to talk much, so I kept it in the very end. But these cladding rods are, again, zirconium is used as cladding, and it's again one of the worst material for the functionality that it should be the best at, because these cladding rods are dipped in water, and zirconium loves to get oxidized if you heat it up. And this is an example of what happens. This is a zirconium alloy pellet at room temperature. If you heat it to 1200 degrees Celsius, it basically becomes cigarette ash. So your metal goes to oxide. Metal is more ductile, ceramics more brittle. Okay. But then other thing happens, and you have Fukushima type of accidents, because now all your zirconium has absorbed oxygen from water. What's remaining is hydrogen, and you can have accidents that we never desire to have. And so people are developing different types of coatings to reduce the oxidation of zirconium alloys. They're trying to come up with new claddings themselves, but it's difficult to replace a single bolt in the nuclear without going through lots of regulations. I won't go through all of these other corrosion effects because they're not linked to the talk somehow. The last thing I would like to say is these are the different capabilities that we have in Liverpool. If any of you want to kind of collaborate in some way, we have good microscopy labs. Because of Nainesh and Suraj, we now have a good electrolysis lab also. And then we have this Materials Center for Innovation, which is Materials Innovation Factory, which houses cryo SEMs and lots of other imaging techniques, including a small angle X-ray scattering, where you can look at small nanoparticles with really good resolution. I think with that, this was a picture. What do I do? I try to do a lot of things, but then I've summarized this in this slide, which is I try to study how materials fall under radiations, or how materials change their properties under radiation. And just to add that radiation is not only used for understanding how it destroys things, but radiation is actually a processing tool in a lot of industries to actually enhance the properties of materials. And that's the direction which we are going. I think Kotari said used to do that quite a lot. And one of the alumni that gave a talk, which is, I think, Mhatre, I think, gave a talk.
Umesh Mhatre.
Yes, Umesh Mhatre. He runs a company which uses radiation to enhance surface properties. And so, yes, so radiation can be used for lots of different purposes. And with that, I think I'd like to conclude my talk here. And thank you for listening. Any questions? I can keep my screen sharing if you need to go on any slides, but if not, I can stop sharing.
There is a comment from Dr. Kailash, and since his mic is not working, Nanesh, can you read that out?
Yeah, just saw it. So he says that Maulik, proud to have you as a student at BRC. So this is his comment, and he has also commented on the question that was raised about the geological sites for the nuclear waste. So
yeah. So basically, so what Dr. Kailash has written is, and this is his expert view because he's been in BRC for a very long time and he spent his whole career over there. So we are still identifying an underground waste storage, but in India, unlike US, we treat sort of nuclear waste as a sort of wealth, and we're trying to do lots of things with it. And so unlike US and India, we are planning to burn the more active plutonium and minor actinides in other fast reactors. And I remember my first bench, or my first office when I joined Dr. Kailash was with a guy called Sanyasi Rao. And they were trying to develop accelerator-driven subcritical systems, which are actually, you can use accelerators to get lots of neutrons. Those neutrons then go and probably cause transmutations much faster, and get the whole activity down to much safer levels.
So if there is any question, they can directly unmute themselves and ask the speaker.
Hello, sir.
Yes.
So, can you, I mean, explain that picture in which you had this picture of palette and there were some fragments around it. So, can you explain those fragments? I mean, it will
What?
be better if you show the picture, I guess.
Okay. Yeah. So it's over here. Let's see if I can go back. Wasn't too far away. This one. No. Yeah, this one. Is it correct? Is that the one?
No, I mean further back.
Stop me when you want me
Yeah,
to
yeah.
stop. Okay.
I mean, it was in the, I guess, yes, yes. Wait, I mean, the third picture, this picture was
Oh,
also,
this one, the picture of the fuel rod. Okay.
yeah, yeah,
So that is basically a cross section of this one here. This one, right?
yeah, yeah,
So
yeah.
this
What
one
was
is
the,
so this is a cross section of a fuel rod, and it has the outer one is the ring of the cladding ring, which is in this case it's stainless steel, and then you have the fuel pellet, and this is after operation in a reactor for I don't know how much time, but after some amount of time. And what happens is, remember I said that we have a huge temperature gradient from the center of the fuel pellet to the periphery. So from here to here, there's a huge temperature gradient. On this side, it is cold. On this side, it is extremely hot. Okay, so this is the center line temperature we call. And when you have a temperature gradient, it's like having a water tank on the 10th floor and you keep the tap open, all the water will go down. So in this case, the mobile species in uranium dioxide is the oxygen. So the oxygens move. There is that porosity. Fuels have an inherent porosity. People make fuels with a known porosity because certain fission fragments, like gases, they want the gases to be accumulated at the top of the fuel rod, which is called as a plenum. So there's a small spacer at the very top of most of the fuel rods, which basically help in accumulating all the gases that are being evolved as a fission products. And so as the temperature rises, you have migration of pores, you have migration of oxygen, you have migration of these cracks, and those migration leads to these changes in the microstructure. At the beginning of the fuel pellet, the microstructure, which is the grain, look like this, where my pointer is, if you can see that. But when you have a temperature gradient, your grain structure changes, it becomes more columnar, and hence, as your grain structure changes, your thermal conductivity changes, and so your reactivity changes basically. So this is a microstructural migration when you have a temperature gradient in a fuel pellet. Does that answer your question?
so sir, can you also explain that void part in which the size of the fuel rod increases?
So this void is there in this case. This is a Magnox fuel where so usually you would have a flat pellet, like in this case. So for example, this one here. So this one doesn't have a hole in it, but these actually, you would think that these are simple pellets that are made by pelletizing, but that actually is a whole mechanical engineering side of making these pellets. These pellets actually have a sort of a dimple in the middle, and they're engineered so that they can take heat stresses, and stresses then can be distributed in the pellet itself. The one that you saw earlier was a fuel that was used in Magnox fuel, which intentionally had a void space in order to reduce these microstructural changes, in order to take this temperature gradient into consideration or so. Okay.
Yes, sir. Thank you.
Any other questions? I'm happy to discuss more.
Can you hear me?
Yeah, I can.
Nagarajan. R. Nagarajan. Can you hear me?
Nagaraj.
Yeah, so Nagarajan sir, your voice is, there's a lot of noise behind it. Hello?
Okay. I will send message to Maulik later.
No, now
Yeah, I
it's
can.
clear. Now it's clear.
Now it's clear, sir.
My first message to you said whether you recall me.
Yes, I do.
Yes,
I think
and
I sent you a private chat saying, hello, sir. I absolutely
I didn't
remember
realize,
you.
I didn't see that, but I didn't bargain for this advertisement which you gave me.
I cannot forget that. You know why? One of the reasons I cannot forget, because the acceptance date of that paper in PRL
Hmm?
is my birthday.
Ah, great.
Not in the same year, not in the same year, but on the same date.
Thank
So
you.
I could never forget it.
The acceptance date is very important because we have a
I know.
priority dispute with the Americans.
Yes, in nature, with RJ Kawa.
But I must confess, I completely forgot in what context I interacted with you. Though I remember you, one of the bright fellows, very likely I wrote a recommendation letter for you also. Am I right?
Yes, sir, you did. So my interaction with you was when I was sort of asked to make deuterium some of the borocarbides through Dr. Tyagi, and then I had to learn the arc melting. So I was sent I was deputed to you to sort of learn the arc melting process, and I think we made a couple of samples, and then basically my whole thesis again was changed to doing radiation effects in some ways.
Anyway, a few Mumbai University students I distinctly keep remembering. One was, of course, Matre. Other one is you. Kavita, I remember to some extent. I think you mentioned her.
Yeah.
Thank you. Thank you for remembering all of us.
No, thank you, sir.
Maulik,
Yes, sir.
Rangwala here.
Yes, sir.
Just have a very general question, which
Sir.
why is it that the developed countries are de-emphasizing nuclear reactors, whereas the developing countries are, sort of, if not sold on it, at least are very interested in establishing these reactors?
In my opinion, I think
because the energy requirement of the developed countries is going to be more. Right? I mean, we are getting into it, but those guys are already into it. So, I mean, so what are the pros and cons of nuclear energy?
So the pros is very well known,
yes.
which is the density of energy that you can extract is there.
Right.
So remember I showed the diagram of the energy trilemma. So in there we have the reason why nuclear energy is still not cheaper as what we would expect compared to any other renewable energy is the following: is that we do have a sustainability because there is lots of uranium, there is even more thorium deposits. So if we go towards using thorium as a fertile, well, so to generate the fissile material, right? Uranium-233, then we can sustain it. So the reliability, the sustainability aspect is there. The two things that nuclear takes a hit on is the safety aspect of things, is the commercial aspect of things, and because of the safety aspect, and because of these our misunderstanding of what a nuclear destruction has done, that has led to a bad public perception, and hence nuclear energy is deemed to be non-safe. However, I mean, there is a brilliant pathologist in London, where she has data of Chernobyl patients from 80s, and it's fantastic to see how many people have died actually to a radiological disease versus, I mean, how much radiation we all still take as background radiation, you know. So that's one. So the pros is there, but the cons are that the public perception is still not 100%, and hence we put more regulations. More regulations means more expensive, and hence nuclear energy is still not a major part of the energy mix. Now, the developing countries, we don't have a choice right now. We do need to increase the nuclear mix, nuclear in the energy mix, because the amount of energy we need is drastically high. And although we can go towards renewables, and we should go towards renewables as well, we do need to have a larger share of nuclear. Any energy mix dependent on one source of energy is not good. You need to have a good mix of everything. Solar, everything. We need to have a good mix of everything.
Thank you. Thank you.
Any other questions the students had or anybody had?
Maulik, can you hear me?
Yes, I can.
Thank you very much for the informative talk. I am from BRC Training School. Even BRC Training School does not teach that much for me. Thank you. I don't know whether they teach now. My story is, of course, decades old.
I'm not sure about.
Did you get Best Teacher Award in the university for you?
No, I did not.
You'll soon get it, I believe. Thank you.
Thank you.
Nice compliment, sir.
Thank you. I've learned from a lot of training school scientists during my years in BRC. So a lot of my knowledge on crystallography and chemistry is brought out from that side. So I'm actually in debt to Dr. Tyagi and to some extent Dr. Kailash in order to sort of bringing those things. And BRC has absolutely provided me like the best opportunity. So, it's one of those places where, I used to always feel proud when I'm still proud of it, because the amount of funding you get, the amount of resources you have at your disposal is huge. And it's just not benefited me, but I have my own batchmates who are now, one is Shirish. So I had my 4 batchmates. One is Shirish, Siddharth, and Sachin. Vivek Parker was my batchmate during masters, but he joined BRC before me, and so a year before me, that is. But Shirish is now a beamline scientist in Brookhaven on the best synchrotrons. Siddharth works in an environmental sciences in US, but he's currently in India. And then Sachin works at the Jack Welch Center in Bangalore. So all of us, I think, had a huge impact from working at BRC, to be honest. And I was one of the lucky ones to actually get to do to PhD. And I think I give that credit to one of my batchmate, which was Ram. I know if others know the name. Ram was a topper in my batch, and he is currently a scientist in PRL in Ahmedabad, in Gandhinagar. And the other is Samhita Joshi. Actually, both of them were before me on the list of people selected for that. And just because they decided not to go to BRC, I was stepped up and hence had a chance to do PhD in BRC, basically. So it all worked out well.